main goal of the meeting is to fit in time. So we are in this introduction, computational, quantum chemistry class. An overview of what the course does. The goal is to get practical skills for computational characterization of materials. One put in theories, one put in atomic models, and then by using right software and the right hardware, one can compute observables and compare them to experiments. Last time, the course is composed of 4 parts. Last time, at the end of each part, we have student presentations. Last time, we learned practical and shared experience how to build models, how to rotate, change their bond length so that you can use it in your research. Now we are computing the basic level of computing electronic properties, electronic structure, basic observables of any model with so-called Gaussian software. And there will be a couple of presentations more. So, once again, 3 minutes per academic presentation, 1 minute to walk to the stage, 3 minutes for questions, 1 minute to go back. It is a very hard task, much harder than to prepare and to present. So try to self-control. Typically, one uses 2 minutes per one slide. Most of you have 10 slides. You need to speak very quick. And skim through slides like crazy. So once again, here is the list. The slides are enumerated. The files with slides are enumerated 1, 2, 3, 4 in the order they should be presented. And just in case, the files are named according to the first name of the presenter. Presenter number 1, Brendon Disrud, who will increase our knowledge in the aspect of what are computational methods and how they are implemented in Gaussian software. Floor.
My name is Brendon Disrud, and I'm going to give a brief overview of electronic structure methods in computational chemistry. First off, what do these do? The most simplest way to say what they do is they help us calculate the energy of the system and the parts of the system and the energy in those. And those will...
Yeah, this one.
Right. And those will help us get some useful outputs, like we can find the geometry, and the absorbance and band gaps of semiconductors and such. As you know from using the Gaussian software, there's a plethora of computational methods, and if you've ever wondered, the abbreviation's got the full name on this side. But I'm going to be focusing on kind of the top of that list there. And let's jump into it. The molecular mechanics method really it's important if you run this that you specify the bonds between the atoms, because it will treat the bonds as if there's like 2 masses with a spring in between. And you can really see that in the energy equation there. It's like, your 100 level physics spring equations for a lot of those terms. And, atoms that aren't bonded together, like 2 different molecules, it'll just run calculations with like Coulomb forces and van der Waals. That's, the easiest to compute. But moving on to what we've been learning a lot in class is the Hartree-Fock methods. The regular Hartree-Fock methods will simplify the many-body Schrodinger equation by a couple ways. Firstly is by having electrons get acted on by a mean field instead of, potentially hundreds of other electrons, making it, a 1 interaction instead of hundreds of interactions to compute. And then you can estimate the many-bodied wave function for all of the different parts as just a single Slater determinant. Based off the Hartree-Fock method, there's a couple others, like the semi-empirical method, which is like Hartree-Fock, but it excludes some of the computation parts and will just substitute in experimental data for those. And then the Muller-Placet, which will run a regular Hartree-Fock calculation and then add in a polynomial at the end with, like when you're choosing the method, there won't be an n, there will be a number, and that's how many terms in the polynomial there will be. Finally, there's going to be EFT, which I'm going to mostly skip over here because we'll be learning about that in the next section of our class. So if you're a guest, feel free to stop by next presentation to get all you want and more. So, in conclusion, there's basically the best in computational cost are going to rank worst in precision. And you really just want to find a balance for how precise you need your results and how long you want them to be running. If there's something that was just more precise for less effort, everyone would use it and there'd be no other methods. So, yeah, that's about it. Questions?
Whitney, please.
So the cost, which one is higher? As in 1 or 5?
1 is supposed to mean better, so it costs less.
Okay.
Where in precision, 1 is more precise. So.
More questions to Brendon? I look at one. So you show the table like 1, 3, 4, 5. It is like ranking in the Olympics.
Yes.
But which time intervals and which percentage or which absolute values of errors you are talking about based on your personal experience? Is it like seconds, days, years, and is it like fifth digit after the period, or it is 200% error? What does it mean? What's the precision?
I guess from just relying off some memory, the cost is going to be different on a pretty large scale. Like your easiest, your molecular mechanics runs might be minutes or hours, and the same, more expensive calculations could take a day or more. And then I assume the precision is going to be pretty much the opposite of that. I don't know how you can quantify precision as easily without actually testing it and graphing it.
Okay, let's thank Brendon for presentation. Next presentation is by HM Faisal Nasrullah, who will share his vision on the question of selection of basis sets.
Hi everyone, good afternoon. This is HM Nasrullah Faisal. Today I am going to talk about on basis sets. So what is a basis set? Generally, a basis set is a set of vectors which defines a space in which a problem is solved. But in quantum chemistry, a basis set is a set of functions which describes the shape of atomic orbitals in an atom. And molecular orbitals are created by taking the linear combination of these atomic orbitals. So from where does this basis set come from? Actually, Hartree-Fock calculation is the most common type of ab initio calculation. The best part of Hartree-Fock is that in it the many electron Schrodinger equation is broken into many one electron Schrodinger equation, and the solution of each one electron Schrodinger equation yields to this basis function, and the accuracy of the calculation depends upon the flexibility of this basis function. The basis functions are usually described by the two types of orbitals. One is Gaussian type orbital and the other is the Slater type of orbital. If you look at the Gaussian type orbitals equation, you look at the e to the power minus zeta r square. Here zeta indicates the width of the orbital and r indicates the distance of electron from the nucleus. And if you look at the Slater type orbital, you look only here is the e to the power minus zeta r, only a r, and this r square dependence is attributed for the less precision of the Gaussian type orbitals, because for that reason it cannot correctly tell the probability of finding an electron near the nucleus. So we can optimize both those features in contracted Gaussian type orbital, in which a linear combination of Gaussian type orbitals is taken to mimic a Slater type of orbital. And if you look that, this is the equation of the contracted Gaussian type orbital, and here we use the contraction coefficient and to mimic the behavior of Slater type orbital. So according to the size of the basis set, it can be classified as the minimal basis set, double zeta basis set, triple zeta basis set. A minimal basis set is constructed by taking a basis function of each type for one type of orbital, and it is the smallest type of basis set. STO, GTO, CGTO are the common examples of the minimal basis set. STO3G is the most common type of minimal basis set. The notation indicates that this basis set approximates the shape of a STO orbital by a single contraction of 6 GTOs. It is the smallest type of basis set. STO, GTO, CGTO are the common examples of the minimal basis set. STO3G is the most common type of minimal basis set. The notation indicates that this basis set approximates the shape of a STO orbital by a single contraction of 6 GTOs. Here are the double zeta basis set and triple zeta basis set. A double zeta basis set is constructed by taking in two basis function for each type of orbital, and the triple zeta basis set is constructed by taking 3 basis function for each type of orbital. So why do we need to use this double zeta or triple zeta basis set instead of the minimal basis set? Because the electron density in a separated electron density of an atom in a separated condition and electron density of atom in a molecule is not the same due to the interactions of other atoms, and so that in a molecule the electron density of an atom can be predicted by the orbital exponent. So if we use more basis function for that, we can allow the variations for these basis functions. So these double zeta or triple zeta basis sets will be discussed in the later type of basis sets. The split valence basis set. We know in chemical environment the valence electrons interact actively, but the core electrons don't. So the core electrons can be treated with the minimal basis set, and the valence electrons can be treated with the double zeta or triple zeta basis set. This is known as the split valence basis set. Popol basis sets are the most common type of split valence basis set, and 631G is the most popular Popol basis set. The notation indicates that each core orbital is described by single contraction of 6 GTOs, and each valence orbital is described by 2 contraction, one is with 3 GTOs and other with 1 GTOs. The polarization basis sets. A polarization function is any higher angular momentum added to the orbit, added to the basis set that is not generally occupied in the separated atom. It is generally used to represent the electron density in the bonded regions. It is generally denoted by adding asterisk with the Popol basis sets. One asterisk indicates that the depolarization functions are added to the non-hydrogen atoms, and 2 asterisks indicate the p-polarization function are also added to the hydrogen atoms. The diffuse basis sets are used to represent the very broad electron distribution. They are important in representing the anions and intermolecular complex. They are generally notated by the plus signs. One plus sign indicates that the diffuse functions are added to only to the non-hydrogen atoms, and 2 plus signs indicates that they are added both to non-hydrogen and hydrogen atoms. Dunning's correlation consistent basis sets. Thom-Dunning proposed correlation consistent basis sets as basis sets optimized at a Hartree-Fock level may not be ideal for the correlated computation. Dunning's correlation consistent is generally denoted by CCPBXZ. CC denotes the correlation consistent, P means polarization functions are added on all atoms, and VDZ, that means valence double zeta, which means the valence orbitals are described by 2 contractions. And if a prefix of is less kept here, then the of indicates that the diffuse functions are also added to it. And here is the Gaussian In Gaussian, we can use the basis set from this group.
Okay, let's thank for a very interesting and very dense presentation. We have chance for brief questions.
What do you mean by increasing the flexibility of the basis set?
The larger the basis set, so if we use the two basis function instead of one, that I use the flexibility of the basis set. If you consider more functions instead of one, there's the flexibility that you can. Okay, in case of split valence, you consider the core orbitals and the valence orbitals separately. There's the flexibility of the basis set.
Okay. If there are no more questions, let's thank Faisal once again. And the next presentation is by Samuel Brown, who will cover the practical aspect that one may need for actual computation of observables for comparison with experiment, related like which observables, which types of calculations can be requested from this Gaussian software.
My name is Sam Brown, and I'll be going over kind of practical aspects of doing some jobs in Gaussian. So my presentation, will kind of go over what the past two presentations talked about with methods and then basis sets. But to perform any calculation, there's three main components that need to be done. So you have the job type, the method, and the basis. So looking into the Gaussian software, we've seen this all before. There's the job type where you have energy, the drop-down menu with various different job types. Then there's also the method that can be done, which was talked about in the last presentation. And then there's also the basis that was talked about, I guess, in the last presentation, the method 2 ago. So job types, I went onto the Gaussian website and pulled up all the different job types that they have: single point, optimization, frequency. So these are some of the different job types that you can do when you pull down the optimization, or just the job types. We've all seen this energy optimization, frequency. These all have different things that they'll do, and there's more than just this. So if you wanted to use a different type of job type that's not listed on there, to do this, you would click into the blank at the bottom, like this, and then you'll type in at the additional keywords somewhere the job type that you actually want to do. And then I'll go on to methods. So this was covered in more detail two presentations ago, but you also have these different methods: Zindo, CIS, SA, CL. These all will do different things, which was talked about. So we can use these different methods to predict different molecular properties. So here's a list that's probably fairly hard to see, but say you wanted to look at the thermochemical analysis, you can do like a frequency type of analysis. Or if you wanted to look at the electronic transition band shape, you could do a freak equals FC. And this is kind of how you do different stuff like that. With a little bit of help, we're going to look at the UV vis spectra of a sample. So I have here 1,3-butadiene absorption spectra. So we've all worked with this molecule, and you can see there's an absorption that goes in at around a peak around 210 nanometers, which is what was calculated. And comparing that to an absorption speed that I just found online, you can see it is pretty similar. So there's plenty of different things that you can do in the software. That was just a brief overview of it. So.
We have a couple of minutes for asking questions.
How many transitions did you do for the 1,3
So I said I had help. I had a lot of help.
Okay.
So, 5. I think I did about 5. 5.
More questions? I have one. So your vision, we didn't cover it in the class, but your vision, what is the difference between ground state total energy calculations that we covered in lab and in the class, and the spectral calculations that you presented right now.
They're higher energy. You're looking at the energy of excitation.
Yes, exactly. No more questions? I think. Oh,
Just a quick question. On the methods, one of them is TDSCF. I'm just curious what that is. What is it? Is it like time-dependent self-consistent?
questions are
Yes.
directed to the.
Okay. TDSCF stands for. Oh, I had it written down somewhere.
Try to slide 6.
No.
If not, in the interest of time, I can ask you later. That's
Yeah,
fine.
I'll have to look it up. I thought I had it.
No, that's fine.
Time dependent self something.
That,
Yeah, that's
that's,
it.
But in general, his answer was correct. That time depends of consistent field is abbreviation for considering excited states. And our next presenter is Jabed Mohammed. He will provide additional insight how to request specific calculation from Gaussian software in case you do not have graphical connection. So it will be more systematic and rigorous lesson how to give orders to the computation program, how to request specific calculations. Floor is yours.
I'm Mohammed. So actually last couple of presentation we know how to do some quantum chemical calculation by using Gaussian software, but we have to give some instruction to the Gaussian software. So for that purpose, we need to make a input file, and we use a graphical software, the Gauss view software, to make that input file. So, and last presentation you also saw that by using some graphical commands, we give them some, and then it will create a file. That's actually nothing of just a SCI text file. So I'm just trying to show you what's their file and how can we modify with that file without Gauss view software, because last time you saw that there in Gauss view there are some default functions and methodology only. But if you want to use a different function, we need to modify that file by ourselves. So this is the one of the typical .com file, and I'm giving an example that I used in our NDSU CCast, not in the USD cluster. That's why they have some extra line here. So they have a 4 section here typically. First section, these are called as a link O commands. It included some hardware requirements and other requirements and program requirements. We put that in the section. And the next section is just a very important line. This line included all conditions, methods, and other requirements for the run. And next section is just identification, just a name. We want to give a name of our job. By that name, we will not get our job in the later on. And the next section, following section, this is a molecular specification. Specification. And in this one, this is an example of a small silver cluster. And the next section sometimes is important, but it's named as optional additional section. Sometimes we don't know that we don't need this section too. So following, just I'm showing elaborately in all section. In the first section, this section started with the percent sign. This percent sign means this is the first section. It includes and the MEM. This means how much memory you want, and give them command. This software will ask for 40 GB RAM memory. And next one is the number of processor, because some cluster they have a default processor, but in our system we can use the different number of processor. Usually Thunder they have a 20 processor in each node, so it's included at 20 here. And Linda, if you want different nodes for a single job, sometimes we need to parallelize this with the node. So this Linda software can parallelize these different nodes, and we can use the more hardware facilities. And last one is just checkpoint file name. Next section. So next section is the command line. Route section. It started with the hash. and hash button means all it will take the command from that line. Suppose like if I give you example, this line is included different is optimization OPT, is can be relief is just given name of the functionals, and is a basis set as you said, as you know, saw that in the basis set presentation. Sometimes we have to use the different basis set, more than one basis set. In that case, if we use a gen command here, that will take a mixed basis set, and we need to define that basis set in the last section, optional section. And they have other comment too. This is the solvent section, what solvent and what's the solvent methods, and how is the core potential, we will read those type of commands. And after that, by blank line, we will be terminate that line. You can use the multiple line, but if blank line means the terminate that section. And we will go to the next section. That's just name of this one. And the same way, just blank line terminate that section. We will go to the next section. First one, in the molecular specification section, first line is the charge and multiplicity of the system. First number indicate the charge of the system. It's maybe 0, -1, +1, or +2, whatever you charge of the system. Space, second number indicate the multiplicity of that system. It's maybe singlet, triplet, or doublet. 1 for singlet, 2 for doublet, and triplet is 3. In the following line, without no space, and the following line, immediate next line, we will give the Cartesian coordinates of our molecular system. If we want to use the molecular geometry from the checkpoint file, we don't need to put these Cartesian coordinates. We can just keep that line blank, and a blank line will make the terminate this section, and we need to put another command in the route section, geom equal to check, then so Gaussian will read the section from the checkpoint file. So same as a one space. Is going to the next section. This is optional section. This is optional section. This is optional section for the molecular connectivity, but most of the case we don't need to use the connectivity for optimization job. So as I said, when you use the mixed basis set, we need to define that mixed basis set in this section. In this section, if you put the different atoms, suppose like this one, and see I want to calculate the silver by using a len L2DZ basis set, and the remaining other atoms want to calculate by using the 631 G star basis set. That's why just I make a list of the atoms, and this 0 indicate the end of the atom list. You have to put the 0 always end of the atom list, and the next line is what basis set you want to calculate. And the 4 star, it indicates this end of this type of atoms, and you start the second type of atoms, list of atoms, and then last number is 0. Don't confuse with the O, oxygen, and 0, sometimes it's confusing. And second star line is end of this line too. And next important thing is, sometimes it's important, you have to put multiple blank line end of this section, because if that means your input file is done. If you don't put the blank line, you will get error messages in the Gaussian file. And you are ready to go to calculations, submit the job. Thank you.
Questions are very welcome to give him hard time. Or learning something about submitting Gaussian jobs that you haven't seen before.
Yeah, right. Thank you, guys.
No, you will not go so easy. So suppose you are computing a very big system, and your cluster has power outage. You know it for sure. And you want to do part of the job today and second part after Christmas.
Yeah, that's the thing, because most of the Gaussian software, they use that what data they already have, they use as a keep that as a checkpoint file. So you can extract that information, what you have done so far from the checkpoint file. In the next run, as I said, you don't need to put the Cartesian coordinates of your system, because you want to that unfinished geometry from the checkpoint file. In that case, you have to put the other route in the command in the route section, the geom equal to check. That means Gaussian will extract the geometry, last geometry from the checkpoint file. So then they will run for the next calculation.
So you can do 50% of optimization today?
Yeah,
and 50%.
But it doesn't work on all calculation. It's work on the optimization job and stepwise calculation. Suppose if you're going to TDFT, it doesn't work. You have to do that because it's a single point job.
Okay, please join me in welcoming Jabed. Mindika Tilan Nakasinki. So he will share his experience about how to interpret the result of Gaussian calculations that have been generated by this code after it has completed. And we are still continuing the game of what would we do if there is no graphical user interface. How to read these plain text files and extract something useful from them.
Okay, good afternoon, everyone. So during my presentation, I'm going to show you some ways to look into the text of an Gaussian output file, to a file called a log file, and it has the same name as the input file, but with the .log of extension, and it contains a lot of different important information in that file. So in this presentation, I'm going to explain how to extract total energy and how to calculate band gap and how to approximate ionization energy and electron affinity using that log output file. So I'm going to use an example molecule, 135 hexatriene molecule, and I performed a single point energy calculation using that molecule for an already optimized structure using Hartree-Fock method. Okay, so I don't have the molecule right now, sorry about that. So first of all, how to weave or how to open a text file or an output file in Linux command line interface. We can use more command to open a text file or an output file in Linux command line interface. So we have to just type more and then the name of the output log file. So we can open the log file and we can scroll through this file using this more command. Okay, so this is the log file, and then the total energy, how to extract total energy from this log file. So this equation gives the total energy of a molecule according to Hartree-Fock theory. This part of the equation represents the electron nuclei interactions, and this part for okay. So this part represents the electron nuclei interaction, and this part for electron interaction. So to extract the total energy from this log file, we can use this SCF done keyword. So first we have to open the log file, and then we can search for this keyword SCF done. To search a keyword, we can use this backslash symbol. So we have to type backslash, then the keyword SCF done, and we can press enter. We can find out the total energy of this molecule. Okay, so there's another simple method to find out the total energy. We can use this command line, the grep command, and then this SCF done keyword and the name of the log file. So we can find out the total energy without even opening the output log file. So next I'm going to explain how to calculate band gap. So the band gap is the energy difference between the highest occupied molecular orbital and the lowest unoccupied molecular orbital. So in order to find out the band gap, we should know the orbital energies of this particular molecule. So to extract the orbital energies, we can use this keyword eigenvalues. We have to just type the backslash and then the eigenvalues keyword. So then we can find out the orbital energies of this molecule. So here we have the highest occupied molecular orbital, alpha occupied. This is the highest occupied molecular orbital, and this is the lowest unoccupied molecular orbital. So we know the energy of the highest occupied and lowest unoccupied molecular orbitals. We can take the difference and calculate the band gap of this particular molecule. So then we can use the Koopman's theorem to approximate the electron affinity and ionization energy of a particular molecule. So this equation gives the total energy of a molecule, and then according to Koopman's theorem, if we neglect this electron interaction term, we can approximate the total energy of a molecule to sum of the all occupied orbital energies. So then we can define total energy of a neutral molecule by this equation. And for an anion, we have one extra electron than the neutral ion. So we have one excess electron. So this expression represents the total energy of an anion. Likewise, for an cation, we have one less electron than the neutral ion. So then to calculate ionization, the ionization energy is energy required to remove an electron from a neutral atom. So in another way, the ionization energy can be defined as the energy difference between the cation and the neutral ion. So it will be equal to the negative energy of the highest occupied molecular orbital. So here we have the orbital energies of these molecular orbitals, and then this is the highest occupied molecular orbital. Then we can approximate this ionization energy of this molecule, and the ionization energy of this molecule is equal to the negative energy of this highest occupied molecular orbital. So for electron affinity is the energy required to abstract an electron to form a negative ion. So in another way, the electron energy can be defined as the energy difference between the neutral ion and the anion. So it will be equal to the energy of the lowest occupied molecular orbital. So this is the energy of the lowest occupied molecular orbital, and we can approximate the electron affinity using this the Koopman theorem. So that's it.
Any questions you always wanted to ask to Koopman or to Tilan? How would this set of orbitals, how would the output file of Gaussian change if you request calculation of a triplet configuration? What would change immediately? What would you see?
Depending on the spin state, it will have two sets of occupied and unoccupied molecular orbitals.
Yes. Okay. Yeah. If there are no more questions, let's thank Tilan once again. And the next presenter is Geerates, who will give a surprise presentation that we completely missed in the labs and lectures, the symmetry of molecules, how it is implemented in Gaussian software.
I'm Zach. All right, so yeah, I'm going to talk about some molecular symmetry applications for Gaussian and Gauss field. But first, we need to kind of get an understanding of what is molecular symmetry. So symmetry is simply an indistinguishable representation of an object in space upon the action of a symmetry operation. So when you apply this to molecules, it's molecular symmetry. Now, what are these symmetry operations? Well, there's 5 of them. One, there is the molecule itself, and the matrix representations are there in lieu of actually having some 3-dimensional figure to show you. The other one is a rotation, which is determined by 2 pi over n, where n is an integer number, so this is in radians, right? Matrix representation. Third, reflection. Fourth, inversion, and then the 5th one is really a product of two operations, where you have rotation and the reflection. Okay, so how do we characterize molecules by their symmetries? We do this by point groups. And so this is a nice little flow chart that shows an algorithmic way to assign point groups for different molecules. I'm not going to go through it because we don't have time. But notice the DNH group here, because I'm going to show a molecule that falls into that point group. More or so for completion, I'm not really going to go over this, but this is a character table. What character tables are is they are complete representations of a point group symmetry in tabular / matrix form. And so the reason I show this is, one, this is the table that people who use group theory to look at molecules can predict molecular characteristics or behaviors. And also on this kind of list here, some of you may have noticed some of the functions in your output logs. They actually have these Mulliken symbols by them. This is where they come from, is they come from the character tables that corresponds to the point group of the molecule of interest. They have meaning, but we don't have time to go over it, unless you want to take group theory, which I suggest some of you should. Okay, yes, now let's go to the actual practical aspect of applying symmetry to the Gauss view. So, very quickly, we start with our benzene molecule, and to get to the point group dialog box, go to edit, point group. Then what you need to do is enable point group symmetry. It's disabled by default. And so what are some of the things one can do? Well, you can constrain your point group or your molecule to a point group. So I chose benzene. It is, as it is, D6H is what its point group is, though the default is always C1, which is virtually no symmetry. That's what that point group means. So if I constrain it, and if I want to perform some operation on it, like changing the bond length, since I constrained it to that point group, it will change the bond lengths for everything, even though I just specified 2 atoms in order to maintain the point group. Okay? So now what happens if I have a slightly disordered molecule, or one that is not optimized for its predicted symmetry? So I started with a benzene molecule that is slightly elongated along or a bond. And so go back to the dialog box. You want to set your tolerance. When you set your tolerance, you increase the really the deviation of the molecule as it is to what it could be. So the greater the tolerance, the higher order point groups you would have allowed to. And so I want to get this to D6H. I select 1.0. Do I feel lucky? Never. But so I can click on this drop-down menu, which will list the higher order point groups. Select D6H, since this is benzene, that's what it is. Click Symmetrize. Oh, hey, would you look at that? We are now symmetric. Okay, so how does this apply to things like doing jobs and calculations? Well, if you go to the Calculate dialog box and click on the General tab, you have this little checkbox where you can actually ignore symmetries. By default, it's unchecked. So every calculation you guys have ever done so far in class, symmetry has been accounted for. However, if you don't, what happens? Well, this is maybe not very impressive, but the conclusion's still the same. So I just did the total energy calculation using Hartree-Fock for benzene, the 321G basis set. So with no symmetry considered, the calculation took 1.8 seconds. With symmetry, took 1.5. Once again, not very impressive. However, if one were to do a more rigorous computation, this would become more useful. What's kind of happening, though, in the background is that if you look at the log file, what's being generated are symmetry-adapted basis functions instead of just the basis function that you were initialized with. So what that means is that if your molecule has symmetry, it will more or less reduce its basis set and then project or perform the operation on the smaller basis set and then project that calculation for the rest of the molecule, assuming that it is symmetric. So, conclusions, you can optimize geometry, not so much bond lengths, more with bond angles, and reduce job time, while maintaining accuracy.
Okay, let's scroll to the very beginning. I will have a question.
Okay.
At the beginning, you did have the Mulliken symbols,
Yes.
and they all have subscripts.
Yes.
So subscripts are either U or G. What are those?
Geerates and Untitled.
Which means
So it means if there's a center of inversion or if there's no center of inversion.
how do you translate it in English?
So, to go back to the initial slide, one of our symmetry operations is an inversion center, right? So if we actually go to the matrix representation, if you go through the molecule straight down on the other side, you should have an identical atom on the other side of that inversion center, right? So Geerates means there is one, Untitled means there is no identical atom on that other side.
Okay, so even and odd.
That works too.
Last chance. If no, let's thank Zach once again. The next speaker is Whitney Ong. Please come and set up your presentation. So she will tell a story of, she will instruct us what to do if the molecule of consideration has too many orbitals, but we still want to look at them and characterize them in average. How to visualize and represent so many orbitals at once. What is yours?
So hi, I'm Whitney. I'll be talking about how to get all of your density states and represent them into a graph. How to generate a graph, Adrian will talk about it later. So let's go through with what the density of states mean. So in general, density of states is the system that describes the number of states per interval energy at each energy level that are available to be occupied by electrons. A high density of states at a specific energy level means that there are more states available for occupation of electrons. A high density of states at a specific energy level means that there are more states available for occupation of electrons. So the script is here. Perl is just to find where the script is. The bin is where the place where you keep your script. And then Gauss, Gap, and DOS version 2.pl is the script name. And then put your file. You have to put a space after that, and then your file name, output file name, and then you put your number of steps, the bandwidth, how many electron volts down from the HOMO, and how many electron volts up from the HOMO. So these are the variables that you can use. So usually steps in calculations I use 1000. Bandwidth you can use anywhere from 0.05 to 0.1 electron volt. And then if you put like, for example, if I put 5 electron volts, then it will calculate from the HOMO 5 electron volts, it will just show in the graph only 5. If you put 10, then it will show more. Same goes for the LUMO. 5 from where your LUMO starts and go. This plot is not normalized. You can normalize it, but it's a different kind of script, I guess. So for example, if you insert this into your command window, that will be your output file name, and .log, which is your output file extension, and then 1000 will be the steps, and 0.1 will be your bandwidth, 5 would be down from your HOMO, and 5 will be up from your LUMO. And then this thing will be generated. So, and then you can see that, you can make sure that, okay, what's your output file name, what's your energy steps, what's your bandwidth, and you can see whatever you have input into this command. And from that, you can also look at your HOMO energy level in electron volts and LUMO energy level and energy in electron volts here. And you can also look at the gap between them without having to calculate it manually. The computer does it for you, which is over here. Yeah. And you can also look at the gap center, where the real gap center in electron volt. I think that's it.
Any questions about density of states? Can you scroll to the image? Will you please show on the image what is the HOMO, what is the LUMO, and what is the gap?
This is the HOMO, this is the LUMO, and the gap is between here and here, which is about 15, I think.
So what's the difference between states and orbitals?
Try it. What do you think?
State can be ground state and excited state, right?
Okay.
Orbital is just...
Yes, yes.
That's right. So the only reason I'm asking is because we call that diagram density of states, but really those are molecular orbitals.
Exactly. It's density of energies of molecular orbitals.
Yes.
The states are more general, those are Slater determinants for ground and excited states. Yep. Yep. Excellent. Third question.
if I wanted to figure out the total number of states within an energy range, what do I need to do? If I use your spectrum, your DOS.
Give me 1 second. So the area under the curve should be the number of states.
Yes. Okay, let's thank Whitney for being brave and answering all questions. So we are moving on with the program with next presenter Aaron Forde, and he will provide additional details on the same subject. So how to convert set of orbital energies into the image. What is behind this procedure, at least from practical side? What is a protocol of converting and how to do it?
So hello, I'm Aaron Forde, and I'll be talking to you about how to use NuPlot to graph numerical data that we generate. So what is NuPlot? Simply, it is a command line driven program that can be used to plot functions or data. And then these are a couple of nice graphs I pulled from the NuPlot home site that kind of show the capabilities that it has. So just as a general overview for how it works, say we have some sort of data file. As you can see, we have 3 columns of data. So to plot the data, we open NuPlot by just typing it in, and then we tell it to plot that file, which is force.dat. And then these 1, 2 specify the number of the columns. So this is saying using this row as your independent variable, and then row 2 or column 2 as your dependent variable. And then it does it again, so you get 2 lines on your graph. And then there are a bunch of other commands that can be used to kind of customize your graph, to give your x and y axis labels like you should any graph, and then give it range, and you can use log axis, and the possibilities are pretty much endless. It just depends on what you're trying to do to plot. And then so if you're going to be generating many plots of the same type, it's kind of tedious just to keep doing it repetitively. So what you can do is you can make a script that you just tell NuPlot to call, and it'll just run through everything and plot it for you right away. So on the left side, this is just a script that I pulled from this tutorial website from Duke. And it sets a scale, it sets x, y axis, gives it a title. And then to call this, you open up a NuPlot in the command line. You just tell it to, you just call the file. And then it gives some sort of output file that you can open, and you get a nice little graph pretty quickly. So for our purposes, density of states is a pretty common chart that we want to look at to get useful data from our system. So picking up from where Whitney left off, we already used the Perl script to extract the density of states data from the log file. And then we have to make sure that we rename that file as dos.log. And that will be specified in a second why we have to do that. So in the command line, we type NuPlot so that we're running NuPlot. Then we tell it where to look, so it's located in the bin in the cluster. And then we tell it which file to look for, which is nuprog_dos_Gauss. And then this is a script that it is pulling from, and it's all 5 lines. And then the important things to look for is line 2. It's set out that tells us the output file. And then DOS-Go9, so we're going to get a PostScript file. And then we tell it to plot dos.log. So that's why we have to rename everything dos.log. Because if it's not named that, it's not going to, it doesn't know what file we're trying to go after. So now if we recheck our directory, we should have a dos_go9 PostScript file. And PostScript file, we don't really know how to open that with a lot of programs or common programs that we use, so we have to convert it to a PDF, which you can just do ps2 pdf write, and then the name of the file. And then after you do that, if you recheck your directory, you'll have a PDF file. You can download that on your local computer, and then you can open it up, and we have a nice little density of states file. So in conclusion, NuPlot is free software that we can use to plot data. You can do 2D graphs, 3D graphs. You can write scripts to make to make it an efficient process to generate our charts, and we can do it in a quick and a convenient way.
Scientific questions you wanted to ask him or ask anyone about density of states?
Oh, first question, can you run this just straight command line without actually entering in a like a new plot script to do it all? Like you can open up a new plot shell type thing? Like if you just type new plot, will it open up the program to run this?
Yeah, if you have it on the cluster, it's locally downloaded on there, so you just have to call new plot, and then it'll run it. But if you wanted to, like if you didn't have it on your local computer, you'd have to download software first.
Well, I guess, because my second question is, I mean, is there a way that if you run it interactively, is there a visual tool that will pop up that you can run off the cluster?
As far as I know, it's just command line driven. There's no graphical interface.
Let me contribute to the discussion. The GNU plot software that Aaron has introduced does have opportunity to do plots.
This one?
Yes. So it does have the set term post, which means the output of this command is established as PostScript file. But you can type set term JPEG or set term X11, which means it will bring everything to the screen. Or if you do not have graphical connection, you can tell set terminal dump text window as a graphic. And then with the asterisks and points, it will draw a very ugly picture, but you can see what it is. Okay? In the, I have one. Can you navigate to the image? And the individual orbitals are represented by peaks with non-zero width. Which physical mechanisms are responsible for this width, or is completely abstract? Request help from the audience, if someone wants to contribute.
Vibration, rotation, they all.
More questions to Aaron, please?
What if you want to compare the homo-lumo gap of different species? So, like in the lab we did different alkenes.
Mm-hmm.
What if you want to compare the gap between having 1, 2, 3, 4, 5?
I just kind of overlay them all. Is that what you're saying?
Is there a way to do that?
It's possible. There are heroes on the internet who have probably already done this.
No, it's in the script.
Okay, let's thank Aaron for being brave and preparing. We have 2 more presentations in the remaining 15 minutes, which seems reasonable. So the number 9 is by Seth Adrian, who will show most beautiful part of this chapter. He will show how to go to visual representations of molecular orbitals in space. And he will tell his own vision of this problematics. Floor is yours.
All right, so we've been talking about molecular orbitals a whole bunch. Let's look at them. I mean, you get nice pictures in your textbook of atomic orbitals. So what we want to do is we want to visualize molecular orbitals. Again, molecular orbitals are linear combinations of atomic orbitals, but they have to have the same symmetry, which Zach helpfully discussed. And the allowness, so how much they overlap, determines how much they contribute to each molecular orbital. And very basically, they can either be constructive, where your wave functions add together, or they can be destructive, where your wave functions actually subtract from each other. And you can see here the C alpha and C beta, that's supposed to be C beta. They are your cofactors for how much they contribute to each molecular orbital. So, construction of your molecular orbital files. So we got a check file out when we run the calculations. You need to change that to a F check file. So use this command form check. I did O2 because it's a very simple molecule. And I have my check file, and then I tell it the output is a F check file. And you get some stuff going on here that tells you, hey, we worked. And then you take that fcheck file and make it a CubeGen file. Now, before you do that, you need to go into your log file, look at where your HOMO is or your LUMO is, because, or what molecular orbital you want to plot, because in CubeGen, you put the CubeGen, which will generate a cube file. You put that command, then you put O for orbital, because we want molecular orbitals. Then you go MO equals, and in this case, I wanted 8 because that was the HOMO for this molecule, the form check file, and then your output. So I called it mo8.cube. But you can, instead of just using an 8, you can use any number that there is an orbital for. You can use HOMO or you can use LUMO, and that will, so then you actually don't even need to know which one it is. You just tell it HOMO and it gives you the HOMO out. So just plotting it, we use Gaussian. It's pretty easy to use. You open it up, you open your file with the cube extension, and then you go to surfaces and contours in the results. And you get this sweet pop-up box here, and you tell it that you want a new surface, and you can modify your ISO value here to tell it, do we want a higher probability or a lower probability? The higher number you put in here, the smaller they get. So if I wanted to, I could plot, very, very small, very, very tight, which is the highest probability area, or you can be huge if you want, fill up your entire screen with green and red bubbles. So modifying for OpenShell configurations is a little bit different, and it was hinted at earlier, but when we run the Hartree-Fock calculation, you have to tell it what the spin actually is. In this case, I was doing O2. As you know, O2 is ground state triplet because it has 2 unpaired electrons. So I had to put it into the triplet state. And I actually ran LAN DZ on it. Here's the molecular orbital configuration. This is calculated from group theory. So it's mathematically rigorous. And you can see 2 unpaired electrons. Let's see how well they actually, or how well it actually goes in calculations. And so the alpha here is all of the up electrons, and the beta is all of the down spin electrons. And as you can see, my occupied orbitals, there's 2 more in the up, and where we don't have those occupied orbitals for the down spin, which is what we want. But there is a little bit of problem because, as you can see here, these are supposed to be, according to the previous, they're supposed to be equal to these 2 right here. So HOMO minus 2 should be equal to the HOMO of the downspin, and it's not. So there's a little bit of calculation error in there. And so when you do the CubeGen for these, you need to change, or in front of MOs, you need to tell it you want the alpha or the beta. You have to put a little A or a B. Say, I want alpha or I want beta. Tell it which one you want. And here's the results of that. Here's the alphas, and here's the betas. So this is the highest, and this is the lowest.
Presentation is open for discussion. Anything you wanted to specify about?
So you're talking about ISO values, and you're saying that the smaller the ISO value, the higher probability the visual represents the localization, right?
The higher the ISO value, the smaller the spheres, or the tighter it is to the atoms.
Okay. So is there a correlation with confidence values?
From my understanding, yes. From what I read and understood was the higher the value, the higher the probability it's in there. Or that's where the electron is at.
Okay, that's...
More questions to Seth? I do have one. So, based on your calculations, you show that the ground state of oxygen is triplet.
Yes.
Does it mean that one can pick a drop of liquid oxygen with a magnet or not?
Liquid oxygen should be magnetic, yeah.
So you can pick liquid oxygen with magnet.
I wouldn't. Liquid oxygen is explosive. If theoretically, yeah.
Okay.
I wouldn't. Liquid oxygen is explosive. If theoretically, yeah.
Okay, good. More questions? If no, then thanks Seth once again. We have the presentation number 10 by Levi Lystrom, who will present his understanding of possibility to analyze charge distribution in a molecule based on Gaussian Hartree-Fock calculations from different aspects, from numbers to visual distributions. Floor is yours.
This is first I'm going to talk about Mulliken charge. And how do we get Mulliken charge in our keywords? We actually don't need to specify with Mulliken, they automatically calculate. So if you see I don't have any pop in here, which pop is for a population of orbitals. So when I use the GUI Gauss view, you can right click and then go down to results, charge distribution. It should say Mulliken. You can choose different things like have a symmetrical range. So for this one I go from negative 0.7 to positive 0.7. And we can see that the outside is a bit less negative or positive, and the core has more electron density. And you can also look at the dipole. So if you click show dipole, it will show wherever it is pointing. If you want to do it in like an algorithm and you want to automatically pull out, do things to it, you can do grep minus a, number plus 1, Mulliken charges, your file tail number plus 2. The reason why you have these numbers is if it's an optimization, it does it twice, so the initial and final. So then for my system I have 66, so then I do 67 and 68, and then it gives the atoms and then the Mulliken charge. So then you can, if you know which atoms are for your core, you can average that, you can do different things with it, and that can be helpful. So another one which is more precise is natural bond orbital, MBO, and here you have to say pop equals MBO. And you can see the difference between Mulliken and MBO is MBO gets a more accurate number. So these are cadmium and selenium, so they should be 2 plus and 2 minus, but they aren't. The maximum is about -1 and -3/4, and that's due to the basis set not being a full basis set. With the approximations we have, they do not always converge, and these are taking the density of the electron and getting a sphere and integrating in that sphere to figure out the electrons around your ion. And a bond orbital does more where the bond is. Mulliken just around a sphere. So electron potential, when you do MBOs, you can open them in JMOL, and you can go to surfaces, and there are 2 different ways you can do it. You can visualize it with the bigger one, or the bigger values, or smaller ones. So we can see here that these are more red, and it's a bit easier to see than this one because it's pretty much all just blue. So I personally like this one. Total density. So similar to the last presentation, to get the total density of the electrons, we generate a cube, but instead of MOs, we do density, and then there's different keywords you can do, and then when you visualize it, you get an electron cloud around your molecule. And I think that's it.
Okay, let's thank Levi for being quick and questions about charge analysis?
I have a semantic question. So
Yes.
is the Mulliken or Mulliken?
Whatever you prefer.
No. The question was, which specific molecule did you use as an illustration for your presentation?
This is a quantum dot. So it's not Mulliken or Mulliken.
That wasn't my question, but okay, that works too.
So this is just quantum dot stuff, so I just pull them open.
More questions? I do have one.
Yes.
So, what is molecular orbital?
It's a linear combination of atomic orbitals.
With some specific expansion
Yes.
coefficients. What is the connection, or is there a connection? What is the connection between expansion coefficients of molecular orbital in basis of atomic orbitals and Mulliken charge analysis on specific atom? What do you see?
I would say that there would be a connection because if you have a high coefficient on a specific atom, then that one electron around it should be attached to that atom, where if you have a very small percentage, then that does not really correlate to around the atom.
So probably you need to take absolute value squared and sum over all occupied,
Yes.
and this will correlate to your charge on the atom.
Mm-hmm.
Good. Last chance to ask questions to Levi. Pay back for him giving someone a hard time. Yes.
What is Mulliken?
What is Mulliken? That is a person, I believe. Who, I don't know who Mulliken or what Mulliken is. Is it a person?
It is a person. Yes.
Okay.
So what does the Mulliken charge mean? Like,
What do you mean by what does it mean?
Definition.
What is the definition of molecular charge?
the Mulliken charge?
It is the electron cloud around the atom, or ion, or nuclei. And if you had a complete basis set, it should converge to the total number attributed to that atom. Does that kind of answer your question?
So what if you got a plus charge in any atom, suppose like you got a plus, what does that mean then? What does that mean then?
I would believe that the nuclear charge is greater than the electron density.
So that number is not electron cloud, right?
So total charge around that area.
Does anyone want to torture Levi further, or it is sufficient? Okay. If no, let's thank Levi. We went through several subjects. I would say very successful. The presentations by your classmates help you to master your skills in running this software. Because you did hard work in preparing, there is no homework, and you get a substantial amount of points towards your final grade. And from this minute, you are entitled certified experts in running Gaussian software. Well, let me thank all presenters, and the meeting is completed. So let me announce the adjourn.